In this video, we're covering the equations of lines and planes in 3D. Let's start with the equations of lines. So in two-dimensional space, we can find the equation of a straight line. Remember, a straight line is of the form y is equal to mx plus c. We can do that if we have two things. The first thing that we need is a point on that line. Right, so we need a point on the line. Let's say a point on a straight line that we are considering is 5 and 3. The second thing that we need is the gradient, which we call m in this equation. So we need the gradient m of that line. Note that the gradient is basically the direction of the line, because if we have a positive gradient, then the line is basically moving upward toward the top right. If we have a negative gradient, then it's moving downward toward the bottom left. So the gradient is basically the direction of the line. And let's say we have an m of 2. So if we had to solve, we'll say 3 is equal to 2 into 5 plus c. And then we will solve for c, and then c is equal to, let's see, minus 7. And then we'll get the equation of the line. So y is equal to 2x minus 7. That's how we do things in 2D. What happens now when we consider a line in 3 dimensions? So to find the equation of a line in 3-dimensional space, we will still need the same things. So we are going to need a point on that line, and we are going to need the direction of the line. However, since the line is now in 3-dimensional space, we no longer are going to use m. We are no longer going to use gradient of that line. The direction of the line will be given by a vector that is parallel to the line. Because if the vector is parallel to the line, so here is my line, and here is a vector indicating the direction of that line. So this vector here is parallel to this line. It is basically indicating the direction of the line that I want to find the equation of. So again, moving from 2 dimensions to 3 dimensions, we still need the same two things. Firstly, we need a point on the line, and we need the direction of the line. However, in 3 dimensions, direction is no longer given by gradient. It is going to be given by a vector. We are going to consider a line, and the name of this line is L, and it's obviously in 3-dimensional space. A point on the line is P sub 0. I'm going to call it P0, and the coordinates are x0, y0, and z0. So they are some specific coordinates on this line, and we are going to call it P0. Take a look at the diagram here. We have the line L, and here is the point P sub 0. Its coordinates are x0, y0, and z0. Next, we are going to have the vector v, and its components are going to be a, b, and c. And the vector v is parallel to the line. So here is the line that we are examining, and take a look at what we have here, the vector v. Notice, or let me do it in a different color. Okay, so here's the line we are examining, and here's the vector v. Notice how these lines that I've just shaded in orange, that is the line that we are considering L, and the vector v, those are parallel. So since the vector v is parallel to the line L, it can be used to indicate the direction of the line. If you recall from the previous slide, that's all we need. We need a point on the line, and we need the direction of the line, and in 3D, the direction is indicated by a vector. So the vector equation of a line, because it is in 3D, we are going to use a vector equation. So the vector equation of the line is r is equal to vector r sub 0 plus t times vector v, where t is an element of real numbers. Now, what does all of this mean? It just looks like an equation. What does each of those individual components mean? So let's go through it. We'll start with vector r0. I'm going to call it r0. So here it is in the vector equation. R0 is a position vector. So just let's remember what a position vector is. A position vector starts at the origin and then goes to some point in space. So r sub 0 is a position vector with the origin as its initial point, hence a position vector. And p0, that is the point on the line, as the terminal point. So let's take a look at it in the diagram. Here is that point on the line. There's p0. Here's the origin. Take a look at this red vector here. That is r sub 0. So all this is in the vector equation, it's just a vector from the origin to this point on the line. So if the point on the line, let's say p0 was here, then our r0 vector would be like that. That's all r0 is. It's a position vector starting at the origin and going to that point on the line. Hence the subscript. That's why p has a subscript of 0, that point on the line, and this vector has a subscript of 0. They are basically matched or linked with each other. Okay, next let's look at t multiplied by vector v. So that is this other component in the vector equation of a line. What is it? So t multiplied by vector v is a representation of the vector v, which is then multiplied by a scalar t called a parameter. Now that seems like a lot, so let's go through it step by step. So here's the vector v, and you can see that this green vector here that I'm highlighting in yellow, it is a position vector because it is starting at the origin. So what we are doing is we are going to take a representation of this vector. That's why it says it is a representation of vector v. Let's remind ourselves what a representation of vector is. It's basically the exact same vector v, just no longer starting at the origin. So it could start here, it could start here, it could start there, wherever in space you want, but its direction basically remains the same. Now, what we are doing is the initial point is going to be p0. That is the point that we have on the line. So we are taking this representation of vector v, and it is going to start at that point 0, that p0 that we have on the line. And that's not all we are doing. We are doing one more thing. We are going to multiply this representation vector that we have by some scalar value t. So t is just a constant number. T could be 1. We could be multiplying by 1. We could be multiplying by a negative, changing the direction. We could be making it longer. So maybe t is 2. We're multiplying this representation by 2. It could be 10, making it even longer. We could be switching it in the opposite direction and making it even longer. So minus 10. That's what the t does. So this representation vector, it could, if I was multiplying it by 2, it could be like that. If I was multiplying it by minus 1, it could look like that, right? So that is what t multiplied by vector v is. It is just going to start at that p0 point, and it's a representation of that vector v, and then we are going to multiply it by some t value, and that's going to tell us how far along this line it goes, or how far back it goes if it was a negative number. And you can see in this specific diagram that t multiplied by v is represented by this vector a. So in case you're confused about what this vector a is, it's basically t multiplied by vector v. Okay, that's also what I have here in the diagram, that vector a, just for the sake of convenience, instead of writing tv on the diagram, they wrote vector a is equal to t multiplied by vector v. And that brings us to the last portion of the equation. So we've covered what vector r0 is. That's a position vector from the origin to that point on the line that we have. And then you know what t multiplied by vector v is. Now, what is vector r? Okay, the subject, what is that? So vector r is a position vector. Again, it's going to start at the origin. So it has the origin as its initial point, and it has the same terminal point as t multiplied by vector v. So here was, so remember a was t multiplied by vector v. There it is, there. It's that black vector on the line. So vector r is a position vector, so it's going to start at the origin. Here's vector r in blue, and it's going to have the same terminal point as this vector a, which is basically t multiplied by vector v. There's the terminal point. So there is vector r. Now this terminal point, why it's special, this terminal point, we'll call it pxyz. That is any point on the line L. So what this r vector does is, it is going to start at the origin, and it is only going to map out points on that line. And how it does that is, you look at this vector t times vector v. When you choose different values of t, for example, t is equal to a half, t is equal to negative half, t is equal to -1, t is equal to +1, you change the value of t. This vector, this t times vector v is going to change its value. It's going to change its direction like so. So it's going to have different points or different endpoints on the line. And now the vector p is going to come from the origin, and it's going to map out all of these points on the line. And as you change the value of t, this vector p is going to spread and spread, and eventually wherever it ends, it is always going to touch this line L. So this vector r basically points to the line L, and it maps it out as you change this value of t. Like I said, this terminal point pxyz is any point on the line L. So this vector r is going to map out the line as you change that t value, which is a parameter. So let's see that a bit more clearly in a better diagram. So the equation r is equal to r0 plus t times vector v is called the vector equation of the line L, obviously because it is in terms of vectors. And since each value of the parameter t gives the position vectors of r of a point on L. Basically, as t changes, as your parameter that you are setting changes, the line is traced out by the tip of the vector r. So let's just take a look at this diagram for a minute. It looks confusing. Here's that initial point that we have on the line. Here is that vector r0. Remember, the subscript zeros, they are linked. What we are going to do is, we already have that vector v, and we are going to take a representation of it. So here's that vector v. We are going to take a representation of it, and it's going to start at p0. But that's not the only thing that we are doing to this vector, this representation of vector v. We are now going to multiply it by t. So when t is greater than 0, you can see here when t is like half, 1, 2, 3, all the way to 10, infinity, this vector t times vector v is going to map out onto the line. And then the vector r is going to map from the origin to all the points on the line. You can see the blue lines here. And then if t is less than 0, right, then the t times vector v is going to map out like this. It's going to move in the opposite direction of this point. And then the vector r is going to map to all of those endpoints. And that's how the vector equation describes this line L. So using the above vector equation, we can equate the components of x, y, and z, right? It's in a vector equation, it's in vector form. So since it's an equation involving vectors, we can equate the corresponding x, y, and z components. So the equations that we obtain are going to be called parametric equations of the line, because they are usually going to involve a t value, and that t is a parameter, hence we call them parametric equations of the line. So here we have it. This vector r, remember, it was just mapping onto an x, y, z value of the line. Then we have vector r0, so that was the point on the line, but now it's a vector, so it's given in components. So it's x0, y0, and z0. And then we have t multiplied by vector v. So vector v is the direction vector, and then we are multiplying it by t. So what we are doing in the next line here is we are just multiplying t by all the components. We get ta, tb, and tc. And then we add these two vectors. So in the first component, we get x0 plus at, y0 plus bt, and z0 plus ct. And then we just equate the corresponding components. So x is equal to x0 plus at. There we go. Y is equal to y0 plus bt. Here, z is equal to z0 plus ct. Last one. So these are the parametric equations of the line. Also, another thing to note, the A, B, and C, because they are in the direction vector, that vector V, there we go, they are called the direction numbers of the line L. So the A, B, and C, those are the components of the direction vector. They are given a special name. They are called direction numbers for that line L that we were considering. Exercise 1. I want you to find the vector and parametric equations of the line W, given that you have a point on the line, and I'm telling you that this line is parallel to the vector V. I also want you to find another point on this line. All right, let's do this. So let's remember the vector equation of this line, of any line in general. So that's equal to vector R plus vector R0 plus t times the direction vector, where t is an element of real numbers. So this is equal to, what is vector r0? So that's a position vector from the origin to the point on the line. So what's the point on the line? It's 4, 3, and minus 1. So it's going to be 4, 3, minus 1 plus t into, what's the direction vector? Minus 7, 5, and 1. So it's minus 7, 5, and 1. And then we just need to have this in its components. So as a single vector, it's going to be 4 minus 70, 3 minus, plus 5t, and then minus 1 plus t. So this is the vector equation of the line. Next, we need the parametric equations. So we need to recognize what this vector r gives us. It's a position vector starting at the origin to any point on the line. And any point on the line, its components are x, y, and z. So all we have to do is equate these components to those. So the x is equal to 4 minus 7 times t. The y is equal to 3 plus 5t. And the z is equal to minus 1 plus t. So those are your parametric equations. Here we go. Let me just square it out. There we go. And what happens if we want to find another point on this line? Well, all we do is we are going to choose a value for t. Now, I don't want you to choose t is equal to 0. What happens when t is equal to 0? Well, sub it in here. You'll get 4, 3, minus 1. Wasn't that the point that you already had on the line? So whenever t is equal to 0, you are going to get that given point on the line, okay? Because remember, it's always relative to that point. You're basically not extending that t times vector times the direction vector, so you are remaining at that point on the line. This basically disappears if t is equal to 0, and you're just getting back that point on the line. So choose another convenient value for t. Please don't choose something like 50. Why would you make extra work for yourself? Choose something like 1. Okay, that's simple. T is equal to 1. So if t is equal to 1, right, let's get a point on the line. So it will be 4 minus 7 times 1, that's minus 3. 3 plus 5 times 1, that's 8. And then minus 1 plus 1, that is 0. There we go. Simple. That's another point on the line. Right, specifically when t is equal to 1, the parameter is equal to 1. Okay, exercise 2. So again, find the vector equation and parametric equations of that line. You have a point on the line. You have its direction vector. I also want you to find another point on that line. Okay, let's do this. So the vector equation of the line r is equal to, we are going to need that position vector going from the origin to the point on the line. Point on the line is 0, minus 10, and 9. Plus our parameter t multiplied by the direction vector v. Direction vector is 8, 3, 2. So 8, 3, and 2 are the direction. numbers. Now let's just put this in a single vector. We are going to get 8t minus 10 plus 3t and 9 plus 2t. That's the vector equation of the line. Then we are going to get the parametric equation. So we need to recognize that that vector r, it's a position vector mapping from the origin to any point on this line M we are considering. So its components are going to be points on the line, and we'll call those points x, y, and z. Now to get the parametric equations, we simply take x, y, and z and equate it to those components respectively. So x is equal to 8t, y is equal to minus 10 plus 3t, and z is equal to 9 plus 2t, where t obviously is an element of real numbers. I forgot to put that down. Okay, there we go. So here are your parametric equations, and to get another point on the line, let's choose again t is equal to 1. If you chose t is equal to 50, then you're probably crazy. So let's get the point. We'll get 8 times 1, that's 8, minus 10 plus 3, that's going to be minus 7. And then you'll have 9 plus 2 times 1, that's 11. Here's another point on the line.